Hi, so what is your name?
My name is Nurin Zahira.
Ainul Bahria.
Ana Shifa.
So I am Hanya Shamimi.
Lisa Hadina.
What course you are studying?
I'm from Kuliah of Medicine.
I'm studying medicine.
Currently, I'm studying optometry.
I'm studying dietetics.
Biomedical science.
Do you know what is catalyst?
Yes, I think if I'm not mistaken, catalyst is something that will speed up a chemical reaction.
I think it is something related to chemistry.
This is the substance that will not be affected before the process and after the process.
That speed up our reaction, the process, and also it doesn't berubah sebelum and after the reaction.
The enzyme that enhance the reaction activity.
My second question is, did you hear about heterogeneous catalyst?
Heterogeneous catalyst. If I'm able to recall my knowledge, I think heterogeneous catalyst involve two different phase.
I don't really remember, but hetero means different, so something different, maybe different in phases, like
For example, liquid and gas.
It's like different phase of catalyst, which is like solid and then liquid.
Like product and reactant is in different phase.
okay. For my last question is, did you hear about catalyst in vegetable oil?
I think one of the example that we can see is in margarine, where it is formed from unsaturated fat to the saturated fat.
Maybe yes.
I don't really remember how does it work.
As a dietetic student, we only learn about the vegetable oil, but I never heard before about the catalyst.
I'm not heard before, but I want to know about that.
Heterogeneous catalysts are in a different phase to the reactant. For example, if reactant particles are in a gaseous state and the catalyst used is a solid state, therefore the catalyst reaction will be heterogeneous. The most common type of the heterogeneous catalysis is for a solid-based catalyst with gaseous or aqueous-based reactant, and the process occurs in the stage of surface adsorption. Heterogeneous catalysts do not undergo absorption. Instead, the reaction only occurs on the metal catalyst surface via chemically adsorbed chemisorb. The basic phenomena start with the reactants arriving at the surface and chemisorb with the metal surface. Next, the reactants are interact and form product and dissolve from the catalyst to the suitable phases. One of the real-life heterogeneous catalysis example is margarine production. Do you know that actually the margarine production is from the catalytic hydrogenation of vegetable oil with nickel catalyst from supported metal catalyst of nickel on silica. The nickel will facilitate the interaction of hydrogen gas with the unsaturated fatty acid of the vegetable oil to form saturated fatty acid of margarine via the adsorption and desorption mechanism.
Have you guys ever wondered how vegetable oil is liquid at room temperature will magically transform into a smooth buttery spread like margarine? This answer relies on a fascinating chemical process called catalytic hydrogenation. This process involves converting unsaturated alkenes into saturated alkene by adding hydrogen molecule into the carbon-carbon double bond using a nickel catalyst. It's a perfect example of how organic chemistry in action, altering molecular structure to change their physical properties. So here how it works. In vegetable oil, the fatty acid contain multiple carbon-carbon double bond. This king will keep the molecule loosely packed, which is why the oil is liquid. When hydrogen gas is added in the presence of nickel catalyst, those double bonds are broken and replaced with single bond, straightening the change and making the fat solid at room temperature. From a practical point of view, hydrogenation improves the texture and the spreadability of margarine, giving it a creamy and butter-like consistency. It also increases the shelf life, making it more resistant to oxidation and rancidity. On a global scale, the process supports sustainability. Margarine often comes from the renewable plant sources like olive, salt, or palm. However, this also brings challenges such as deforestation that link to the palm oil, while highlighting the need for responsible sourcing. Next, for the industrial, hydrogenation offers amazing flexibility. Manufacturers can control the degree of saturation to produce different fat profile from soft spread to baking shortening. And due to health concern over trans fat, the food industry is now innovating new techniques to make margarine healthier without compromising quality.
Let's move on to the next segment where I will be talking about the recent advancements and research in nickel catalyzed hydrogenation, particularly in the context of vegetable oil processing and biodiesel production. So let's begin with the first catalyst development, which is the nickel titanium dioxide, where it already shown excellent performance in soybean oil hydrogenation, achieving high turnover frequencies and reducing trans fatty acid TFA formation to as low as 10.5%. This is due to the high dispersion of nickel nanoparticles on the titanium dioxide surface, which enhances both activity and selectivity. The second one is the modified nickel silicon dioxide catalyst. With the little addition of ceramide dioxide, it can further improve hydrogenation by increasing activity and favoring cis monounsaturated fatty acids. Serum oxide acts as a promoter, enhancing the electronic interaction and dispersion of nickel. The last notable breakthrough is the carbon-nickel bentanoate catalyst. This catalyst is prepared by using an ammonia-assisted impregnation method. This system achieves a 75% conversion of linoleic acid methyl ester and improves the oxidative stability of biodiesel from 6.5 hours to 18 hours. Nickel-based catalysts, especially when supported on advanced or modified materials, they offer a variety of advantages and also disadvantages. From an environmental perspective, these advanced supports like titanium dioxide and silicon dioxide not only enhance catalytic performance but also help minimize undesirable byproducts such as trans and fats. Economically, nickel is cost-effective, especially compared to precious metals like palladium and platinum. However, some forms like rainy nickel, which are pyrophoric, they ignite spontaneously when exposed to air, raising handling and safety costs. On the societal side, the reduction in TFA content aligns with the global health guidelines, promoting safer foods, products, and cleaner fuel alternatives. Yet, it's worth noting that all the nickel catalysts can still produce high levels of TFAs, up to 40 to 50%, which pose significant health risks.
So now, let's look at how the heterocatalysts connect to chemistry concept in the hydrogenation of vegetable oil. So first, from a thermodynamic perspective, hydrogenation is an exothermic process which releases heat to the surrounding. The enthalpy change is negative and so is the entropy change. Because of this, the reaction favors high hydrogen pressure, which shifts the equilibrium towards the saturated fat product. This aligns with Le Chatelier's principle. Moving on to the reaction kinetics, the rate depends on factors like hydrogen pressure, oil concentration, and also the catalyst surface area. The Langmuir-Hashwood mechanism plays a vital role in this reaction. It describes how both of hydrogen and the oil molecules adsorb onto the nickel surface before reacting. Nickel lowers the activation energy by offering an alternative pathway, and not to mention, silica support also help in the reaction by keeping the nickel from aggregating, or what we call as clump. It helps maintain a high active surface area of the catalyst for the reaction. However, there is also a challenge in this reaction, which is poisoning. The sulfur produced from the crude oil can block the nickel active site, which reduces the effectiveness of the catalyst. Next, if we break down the Langmuir-Hashwood mechanism in details, first, the hydrogen molecules will adsorb onto the nickel active site. The nickel will break the hydrogen bond of the molecules. At the same time, the C double bond also adsorb onto the nickel surface. The reaction only happens on the surface, which when the hydrogen atom attacks the C double bond and forming a half hydrogenated intermediate. A second hydrogen completes the hydrogenation, forming a saturated fat. Finally, when the product is finished, the saturated fat will deadsorb from the nickel surface, leaving the nickel site to be free, and the catalyst is ready for the next cycle. In terms of green chemistry, this catalyst is very valuable because it is a solid spotted catalyst. This means that the catalyst can be recovered and reused, hence reducing the waste of the reaction. The reaction condition also moderate, which make it less energy intensive, and silica itself is innate and environmentally friendly. For industrial scale-up, feedback or trigger back reactors are commonly used with this catalyst for continuous production. Both nickel and silica are affordable, and widely available, and the catalyst also lasts long, especially when regeneration systems are in place.
To conclude, the knowledge of catalysis can drive industrial efficiency and the quality production that aligns with SDG Goals 2, Zero Hunger, and SDG 12, Responsible Consumption and Production. The selection on the heterogeneous mechanism and the type of solid catalyst of nickel on silica result in the conversion of vegetable oil to margarine with benefit on enhancing product quality and the reaction selectivity.